Good afternoon. Welcome to the RAL seminar series for today. And we'd like to welcome Dr. Marina Astitha of the University of Connecticut, where she is an associate professor and also Eversource Energy professor in environmental and sustainability education at the School of Civil and Environmental Engineering at the University of Connecticut. She is also an affiliate scientist of NCAR, and we welcome her annually for a visit. We've had a great week with her. She'll be here through today and Friday morning as well. So if you want to chat with her, please make an appointment. She has an office on the second floor of this building. So she is also an associate editor of AMS's Weather and Forecasting Journal, and she mentors a lot of students. So let's welcome Marina.
Thank you, Sue, for the warm welcome. It's always a pleasure for me to be here. It's kind of my happy trip every year, and friends around the room know that I'm really excited to be here and give the seminar to you. As Sue mentioned, I come from exotic Connecticut. University of Connecticut is the state university for Connecticut. I have been there since 2013. I have a lot of undergrads, graduate students, and postdocs right now in my group. And a lot of the work you're going to be hearing about, of course, is the work of graduate students, PhD and postdocs. So before that, a little bit about me. This is the few pictures of my family, my silly dog, Bailey, our trips in Greece, just to get you jealous a little bit because it's summertime. And I'm originally from Greece, obviously. And the name of my research group, Atmospheric and Air Quality Modeling Group. I'm going to talk about extreme weather forecasting today, so I'm not going to spend a lot of time on that. But I want to give you an idea of other research topics that my group is working on. Another one, a second one is offshore wind resource assessment. We have some funding from DOE, NSF, IUCRC, and the utility, Eversource Energy, is one of the largest utilities that handle the Northeast. And they had a consortium with Ørsted for building the South Fork wind farm, for those of you who know about WFIP3 and all that. And what we did, and we're still doing with that, is developing high resolution WRF simulations, using 3D PBL, and assessing turbulence and hub-height wind for that North Atlantic offshore area. We have done some climate change assessment, impacts for wind energy specifically. This is a collaboration with Ethan Goodman here at RAL, using their statistical downscaling technique. And just to highlight what that looks like, downscaling ERA5 and CNIP6 models into a 4-kilometer resolution to address and assess primarily wind energy changes in the future. I'll be happy if you guys want to interrupt at any point and ask questions. That I love when this is more interactive and I don't talk by myself for 30 minutes. All right, a little bit about my collaborations with NCAR over the years. As Sue mentioned, I am officially an affiliate with RAL since 2022, but collaboration started earlier than that, with Stefano, with Luca. You guys see your pictures, your photos up there, yes? Okay. Hope they're current, they're not very old. Some are not here anymore, some might leave soon, but still, I'm very, very proud of all the collaborations we've built over the years. And it's not just about the research, it's also about mentoring students. And I'll tell you what, my students love working with NCAR folks and have the opportunity to be here for maybe a month over the summer or not, doesn't matter. It's something that changes their trajectory because it gets them into that networking. So I'm pitching that to you. If you're interested in, I know a lot of you do that anyway, working with graduate students, that's great. You can ping me. So some of the common research areas we've worked collaboratively in the past is storm prediction with the analog ensemble when Luca was here and with Stefano. Offshore wind forecasting, as I mentioned, wind routes, 3D PBL, approximation into WRF, wind speed climate assessment, wind gust prediction and uncertainty. You're going to hear about that today. And snowfall prediction improvement, which is the other part of my talk today. I haven't collaborated with anybody for snowfall, so if I have any takers, please let me know. These are scholarly outcomes. So what have we produced together? These are just the papers that I have in collaboration with you guys. And these are a couple in prep, one under revision, and the rest are already published. These are journal papers, and these are some conference presentations. I'm very happy to show all that. So now going into the sciencey stuff. Extreme weather, why do we care? All of you know that extreme weather is really impactful. I usually show this slide just to make a point. If you look at the green color, shows severe storms. This purple is winter storms, right? And a lot of that shows us when it happens for every month of the year. So severe storms are really there most of the time. And over the years, we've seen an increase of those events. This is from the very well-known billion-dollar weather impacts that might go away very soon. So I wanted to grab that from 2024, showing how the uptake of cases, these are just number of events, starting in 1980 all the way to 2024. All right, why do we care up in the Northeast about that specifically? The impact of extremes is what we care about. So what you see on the right is a picture of a downed tree during Irene, tropical storm, big thing. But it's not just tropical storms or snowstorms that are really impactful for us up there. These are all real photos of how the impacts on the power distribution network look like in the Northeast. But again, besides the big tropical storms, they may not come land over there. We also have even a severe thunderstorm can cause problems like that. Down trees, down power lines, customers out, hopefully for a few hours, but sometimes for days. And I am affiliated with the Eversource Energy Center at the University of Connecticut since before its inauguration in 2015. This is a partnership between the utility and researchers at the university, and there is an operational flavor to that. So we run WRF 4 times a day at a 4-kilometer resolution. We provide all these wonderful variables that are impactful for weather-induced power outages. We manipulate them a little bit. We kind of cut out the time sequence of that. So you have the maximum gust, maximum sustained wind, total precipitation, and a bunch of other variables. And all those feed into outage prediction models, machine learning models. And this is what I'm showing you now is actually a current forecast for tomorrow. We're expecting some severe thunderstorms Thursday night into Friday. And we issue this not just for Connecticut, for a lot of other, for Massachusetts, New Hampshire, we have a lot of other territories, but this directly goes to the emergency preparedness managers. It goes to them with some range of variability, not just the map. So you can understand that if the weather is not right, those outage prediction models are not going to get it right. So it's imperative for me as the weather person to be able to improve when things need to be improved. The first part that I'm going to talk about is prediction of gust. So over the years, we started this connection of weather with outages when I first came to the university 2013, very, very slowly, with so small amount of data for the machine learning models to make any sense. And it was clear from the beginning that gust is a very important variable for that, highly impactful. So the first part is a paper published in in Artificial Intelligence for Earth Systems in 2024 by my PhD student, Ishrat Jahan. And what I'm giving you here is the motivation. Why is there an issue for addressing this? This is the WRF output for 61 storms through UPP, the only way to get wind gusts, directly as a variable, even though it's parameterized as from UPP, which is not wind gust, is a high gust potential. And of course, that doesn't work for us because even though this is pretty good, high gusts with parameterized predicted by UPP is okay, this is a big problem, and this is a big problem. So when you give an input into the outage model that is so highly over-predicted, then the outages will be definitely highly over-predicted. Not linearly, but in some manner. So it is important for us to produce something that is not that highly over-predicted. In terms of the methodology, we have a 4-kilometer WRF domain, showing you the ISD weather stations that we used to train the model. This is also the distribution of gusts, the right tail, right skew distribution, as you all know. And we used an older version of WRF at the time because we are running WRF and in forecasting mode, but also in analysis mode, and we have tons of storms since 2004. Maria was there in 2013, 12, right? You were responsible for that. So that's something, that's why the version of WRF is a bit old. We tried the random forest algorithm and the XGBoost, a lot of leave one storm out cross-validation, hyperparameter tuning. I'm not going to go into these details. I'm happy to discuss them afterwards, just to give you a flavor of the technological path going into that gust prediction. On the right, you have the variables that we used as features from WRF in the model. And of course, to get down to that list, we did a lot of feature exploration sensitivities to get down to wind speed at 10 meters and 850 and 950, planetary boundary layer height, friction velocity, some wind direction components, terrain, and some lapse rate components too. All right, going into the results. WRF UPP again on the left. In the middle is the random forest prediction, and this is the XGB. So you can see that, of course, it took care of the over-prediction a lot, but it kind of struggles to get the high-end wind gust values there. In terms of bulk statistics were good. XGB has reduced all the error metrics greatly. We love it, and statistically significant results. This is bootstrapping for all the different simulations. We also did some linear regression, GLM techniques as a reference, but I'm not going to show all that to you today. I'm going to just focus on the machine learning aspect. So in terms of the bulk 61 storm prediction with a leave one storm out, XGB is statistically better. If we want to see the performance spatially, on the right you see WRF UPP, mean absolute error in RMSE, everything is in the red, so 4 and above meters per second. Errors and XGB, I'm going to talk about XGB from now on, is the one that kind of gets it right. Much better, at least. This is not enough when we're using machine learning, and I'm not an expert in machine learning at all. I'm a physicist by training and a hardcore physics-based models, person, so it took a while for me to get into, this is a cool tool, let's see how we can utilize it better. Explainable AI techniques are paramount for me. It's really important to understand if the model gets at least what we know is true from the physical processes perspective. And we had a question, is it 61 storms? Maybe not enough. Wind gust is intermittent, doesn't happen all the time as precipitation. So we wanted to test how many storms might be enough, and that's what you see here in the learning curves on the left. And I can just show you, actually, MAE is one of my favorites, so higher, just 5 storms at the beginning for the training, and then adding 5 every time, at some point you reach a plateau, and the results are not statistically different anymore. So that was a good lesson. Traditionally, you always hear about, well, you know, you need more data, right? That's machine learning. You need more and more data, and I fully understand that. But how much data is enough? It's still a question mark, for me at least. Permutation importance plots, these are just a sanity check, nothing more than that. I mean, we know wind at 10 meters should be very important for wind gust, and the model picks it up. Great, that sounds good. I was happy to see that U star, the friction velocity, was there too, which is expected, and then the machine learning model got that too. So that was a good sanity check, and we do that. I'm not going to repeat all these plots every time, but that's something we kind of traditionally do. So this conclusions from this study was that both random forest and XGB do a good job in correcting the overprediction. We know they can remove the bias really easily, but they also removed some other random errors through CRMSC that we tested. But again, it's faster than the normal method, but the problem with the underprediction of very high winds, very strong and damaging winds, this limitation is still there. Any questions while I finish this first part? All right. Moving on. So what do we do next? It was, to me, it made sense. It was logical to try a neural net. And then I met these great guys from Miles that are in the room, and we said, why not try ENN, the evidential neural network? The objective was not to improve necessarily the prediction of gust. All of us did not anticipate a great increase, but the added value is the uncertainty characterization. To me, that was an amazing advantage. Now, a few things changed from the previous study. We added the New York State Mesonet data there to increase the number of observations, and we have a newer version of WRF that we rerun all these 61 storms, basically. This work that I'm discussing now is under revision with environmental modeling and software. We got 4 reviewers, guys. I don't know, 4 reviewers. How many of you get 4 reviewers? Okay, moving on. What do we do with that? I'm not going to get into the details of VNN. I'm not the expert. Ask DJ and John. So that's easy for me. I'm going to explain to you how that worked for us, for gust. You get your WRF features, you get your ENN, your observations, you train them, hyperparameter tuning. Ishrat really didn't like that. That took a lot of time. In the end, though, you get your gust prediction, but you get your aleatoric and epistemic uncertainty and the total uncertainty, for that matter. And because so far and throughout, I'm going to be talking about deterministic forecasting, we know this is not the best we can do. So having a range of variability of the outcome is really important in us going forward. The variables, the features from WRF are pretty much the same, few changes here and there. I don't think I need to mention any of that for now. The only thing I want to mention is that for gust, epistemic uncertainty was 3 or 4 times higher than aleatoric, so I'm going to be talking to you about total uncertainty in the following slides. Results, WRF UBP at the top and evidential model prediction at the bottom. Right? Pretty much the same features that you saw before, the same pattern, the prediction. So it kind of does similarly with XGB, but that's not why we wanted to use it in the first place. I also wanted to show you this nice diurnal plot. This is over all the storms, 61 storms. hour of the day, actually storm hours specifically, and in blue are the observations. This green is WRF UPP, and the orange is the ENN. So you kind of see, first of all, we know there's no diurnal cycle. That's okay. We wanted to see if there is a variability change in our predictions. And you kind of see very nicely that ENN gets really close to the median value, very close to the distribution, kind of shrinks the distribution a little bit, doesn't have the variability. But look at the variability of WRF UPP. That's a lot of range there throughout. It applies to all the hours and all the data points that we had. We've tried other techniques like SMOTE to do kind of artificially bring more data into the model. They did not statistically improve anything. In some cases, they kind of drop down but I'm not saying this is final. There are a lot of other techniques we can and we should try. So here's what I really loved. This slide that has a bunch of figures that I thought it was really phenomenal for our simulation. Running one simulation, get the gust, get the uncertainty without an ensemble, right? Without running 100 or more different simulations. So we are able, with that uncertainty value for gust, we are able to construct statistically a range, a lower and an upper range of that gust value. And this is a storm, an hour of a specific storm, actually at the height of the storm. This is the gust prediction for the hour, the lower boundary and the upper prediction boundary based on the uncertainty that we get from ENN. I don't love the color bar, but unfortunately the reviewers want us to do something like this, so you gotta stay with that. And I'll talk about the gray points, the gray areas in a minute. This is 24 hours after. So this is when the storm has almost finished, passed, so you kind of see the same thing. Prediction of the hour, lower boundary of that prediction and upper. And if we're gonna look, I don't wanna do that anymore. If you look over Connecticut, you can get up to 10 meters per second for gusts, pretty high over the Connecticut River Valley. And then your range is between 7 and all the way to 14, right? So it's just a very helpful information, especially if you are a planner. The gray areas are the areas that the uncertainty was very high, unrealistically so. So we defined those as not acceptable, not trustworthy. Okay, so gray area is something that you don't want to look at. Now, where does that high uncertainty coming from? That's the important information I always wanted to be able to tap into without running a lot of sensitivity tests with WRF. The top plot on the right shows you total uncertainty, maximum total uncertainty, and storm intensity. And we'll use the maximum surface wind speed as a proxy for that. And it was striking to see this type of high correlation on an almost exponential scale. So what I originally thought that probably those variables that we use for the training of the algorithm that are not really important, that those are the ones that are bringing a lot of uncertainty, and of course I was totally wrong, is the high influential variables that bring that high uncertainty. The other very interesting part was total uncertainty versus spatial gust gradient. So when gust changes rapidly from one grid point to the other, that's when the uncertainty also picks up, which is probably a feature of the gridded scale models that we have. And we need more time to think what that means and how we can capitalize on that. Explainable AI techniques, again, permutation feature importance on the left, both for the gust prediction. Where are you, pointer? There you are. This is the change in RMSE for gust, and this is change for the uncertainty. And they kind of agree. The higher friction velocity influences the model a lot, same for the uncertainty. And wind speed, Of course, we're expecting that. Same for uncertainty. Again, kind of a sanity check for us. We use plots like PDPs. I don't love PDPs or ALEs, just to give us an idea of whether the model understands the physical processes that we understand, at least we have good knowledge about. So in terms of some conclusions from this work, we're really excited that this type of modeling can give us those uncertainty, the ranges of uncertainty that a stakeholder, a practitioner can actually use, can have that range of variability in front of them and make decisions based on that. We looked at key features that are really important for the prediction of gusts, that are also very influential for the uncertainty, and they can cause that. Epistemic uncertainty was much higher than aleatoric, which tells us maybe some model availability of the data in that range. The higher gust, we can still not get it correctly. All of that matters. And still challenges, because we're talking about successes and challenges, right? Challenges on those the higher end of the distribution. All right, that was for gust. And I'm going to take you into snowfall, a little bit of winter weather. As I mentioned at the beginning, again, during winter time, snow accumulation and density of snow, how wet or dry it is super important for the impacts in the grid. So the objective here was try to see if we can forecast the snowfall accumulation a bit better or faster, or just to try it out. It's not like WRF doesn't do a good job. Actually, lots of the times does a good job. And I'll show you both cases where there's no need for change. This paper is published in Journal of Hydrology. This is Umul Kaira. Umul graduated last year. She's a postdoc now in my group. Greg Thompson, Diego Sarai from UConn, and myself are the co-authors. So here's one example. You have this 2015 snowstorm. Most of the snowstorms I'm going to talk about are nor'easters. Maybe we'll have one Alberta clipper, but that's about it. Most of them are Miller A's and Miller B's. We're using the National Snowfall Analysis product on the left as our reference. I'll talk a little bit about that. And this is our WRF AFWA output. I know that's not great to use snowfall from AFWA, but it's kind of what we've been doing so far. So the model really said, over-predicted by a lot and did not get the whole extent of the accumulation. Another one in 2021, you see the beautiful coastal band there of higher snowfall accumulation. Sorry, I don't have my, So these colors mean there's a lot of, very heavy snowfall accumulation. And for this one, the model really didn't get anything. And this is an actual event we're analyzing with a new student of mine, because even the Weather Service could not get it right at the time. So it was a pretty tricky event. Unfortunately, we're seeing some weird things with solar radiation. And in the WUSA meeting yesterday, you guys kind of talked about that. So there might be something going on with that. So that's the motivation of the methodologies, again, decision-based models, decision trees, random forest, XGB. Similar setting. The difference here is that because we're using this gridded product, the National Snowfall Analysis, we wanted to evaluate it first against in situ observations to make sure that we're using a trustworthy gridded product. And that's what it looks like. Pretty good. 45 variables from WRF. What else I want to show you? A little bit of the variables, some static ones, latitude, longitude, terrain height, and then all the variables that are in here do not include snowfall, right? These are based on the processes we understand that move into snowfall accumulation. We wanted to see if the models can get it right. The bigger one is, the more important one, of course, is liquid water equivalent, which is included. All right, what do? Get the features in. from WRF, get your NSA product as a reference, and do a lot of feature selection, hyperparameter tuning, training the models and all that. The only thing that's different now compared to GUST is that we have a two-step approach. We have a classification, snow and no snow, so we don't have a lot of zeros in our data set, and then we move into regression. Leave one storm out, etc. So here is that 2015 weird snowstorm, weird in terms of how the WRF was able to capture it, right? That's the one, this is NSA, and then random forest is able, both XGB and random forest are able to correct that over prediction, but then they don't get anything like in southern England, they don't, there's nothing there, right? So that's still, all the numbers, the bulk numbers look great, a huge amount of reduction in the errors and increase in correlation, but we still don't like it that there's nothing where it should be over Connecticut. These scatter plots are for all the storms, 31 validation storms, so showing you again bulk statistics. On the left, where are you, pointer? This is the WRF. No, it's not too bad, but that bimodal distribution is something it affects us in terms of how that moves into impact modeling later on. So when you look at the WRF random forest, kind of gets a lot worse here, and the XGB is doing a better job. And statistically, through bootstrapping, again, the XGB is showing statistical improvement overall. Now, from the operational perspective, bulk statistics don't say much because we need to be able to forecast the storm that's coming as accurate as possible. So we needed to look at all the individual storms and how the models predicted. This is not it's not a figure that you want to look at. Your eyes are going to hurt. So it's just to show you that we analyzed each storm. 27 out of 31, the errors were reduced with the machine learning model, which was great, the overall errors. But there are best cases and worst cases. So, being into the transparency, I'm going to show you two best machine learning snowfall cases where the algorithms did a great job and two that it didn't. And I'll explain to you why. At the top is a February 2022 event, NSA. This is what WRF thought, like a lot of snow, much higher than the reference. And then random forest XGBoost do a better job in correcting that. And actually, that was the great thing about it. Even though they over-predicted, they kind of understood there is some extent of that snowfall on the south, which was a good sign. Right, that part, we're also always looking at liquid water equivalent from the model and from stage 4, just to make sure to understand what might have caused that over-prediction with WRF. And it doesn't really, the liquid water equivalent doesn't explain this really high number here. At the bottom, another storm, very high accumulation of snow over the lake, Great Lakes, and New York State. The models, both machine learning models, were able to kind of remove that, and that's probably coming from a very high liquid water equivalent that the model is showing there. But these are one of the best cases. The reduction of that over-prediction is really optimistic. And I'll show you two worst cases where the machine learning model really couldn't get it. And that is at the top, NSA, this is 2013, February. The model, WRF did actually a pretty decent job here. There was no real need for changing much. Probably for us in Connecticut, there is this area in western, central Connecticut that was impacted more. But random forest and XGBoost are really not there at all. They can't get it right. The one at the bottom, again, pointer? There you are. So this is, again, a nor'easter. WRF is A-okay, not great, but then both algorithms kind of push the extent of that event much higher than what it was. So, but there is a reason for that, under prediction, over prediction, and all that. Both of those events, where's my last one? The one on the top was a bomb cyclone. The other one was a rapidly intensifying storm with a 14 degrees Celsius difference in temperature, crazy number. So when you have these events, and we are probably, I should have mentioned more specifically from the beginning, these are based on 24-hour features and observations, 24-hour accumulation. So after seeing this, we were almost convinced that because we're using a 24-hour output from WRF and our observations are on 24-hour, there is not a lot of room for the algorithm to figure out those really rapid changes in a dynamic system. And if the changes happen in less than 24 hours, within 6 hours, and I'll show you what we did about that, that makes a big difference. I'm going to push because I don't want to take, it's 1:38. I want to be mindful of the time so we can have a conversation. So the next Journal of Hydrology paper was exploring that, the temporal frequency of the inputs and how would that impact those storms. Pretty much the same structure. I don't want to bore you with all that. We changed a few variables here and there, but nothing big. Now, from 24-hour accumulation, we're going to 6. We are bounded by what the NSA is providing. There's nothing less than 6 hours. So you see on the left, these are aerometrics, correlation, RMSE, MAE. This is the XGB 24-hour. So you don't see a lot of big changes. Actually, the correlation drops compared to WRF. Same with MAE. But we see a better condition with the 6-hour, this is just for the validation storms here, and a better MAE overall, which kind of said, okay, now it's getting something right with these rapidly intensifying storms, statistically better for the 6-hour model. Want to show you a test case. So this is the 2013, which WRF did pretty well. This here underpredicts, I showed you this before, this 24-hour model, but the 6-hour model, look how beautiful it is in building. It doesn't get to where it should be, but at least it builds something. There's a pattern there that it recognizes. And that also manifests really nicely in the scatter plots at the bottom, where you see the 6-hour kind of building a nice rapport there with the observations. That's another one. I mean, sorry guys, have you ever seen this? Like, I haven't in my life. I couldn't believe there's like one-to-one relationship almost. But this is a storm that WRF actually got it pretty well too. So it's not surprising. This is the original snowfall accumulation, and then we get a really nice improvement, whatever there was here with the machine learning model. Last one, I'm going to talk about inputting probabilistic weather for, snowfall accumulation data in the model. That's something I wanted to do, and we got the data from the Weather Service, so we wanted to see if we can actually predict the bias of snowfall accumulation better than the actual accumulation. So I want to move on just to show you the cases and wrap it up. 33 validation storms. This is WRF AFWA, correlation and MAE. XGB kind of struggles, doesn't really do much. And then those storms that have the probability of above a particular threshold of snowfall in percentile data in it kind of gets it really nicely. This was a very, very nice outcome and a reduction of the error. This is a test storm. The previous one was for the validation storms. And we also tried some classification schemes. I'm going to skip that for the sake of time. This is the NSA for this particular February 2024 storm. This is the WRF, so it kind of missed a big amount of snow in the Connecticut and Massachusetts, then the 24-hour model doesn't really get it. The 6-hour model does, which was beautiful to see. So it's all about understanding the limits and the advantages of using these machine learning models. I want to go beyond that. The only thing I want to mention is that for the heavy snowfall cases, really, we have about 7% of the data that are above 200 millimeters are really strong cases. So it's, no matter how many storms we put in there, that number is not going to change. To summarize, I wanted to discuss with you today about the synergy between physics-based models, machine learning, and AI as new tools, and how we can, how in my group we try to use them the best way we can, exploring errors, uncertainty, and finding new ways to maybe understand processes we don't fully understand. And embracing that, again, is something that we want to do for the future of weather science, I think. But equally important, continue developing a physics-based models at the same time. To me, this is super important. We should not forget that. Supporting everything with this assessment that's statistically rigorous, and at the same time, you have all these explainable AI techniques is where I think we should go. Questions? I hope you have a lot.
Okay, great. Inviting questions now, both virtually via Slido as well as from the room. Who would like to start?
Who's the brave one?
Stefano.
Yes.
Good catch. So Marina, I noticed that, also in my experience, I see that when you train these machine learning techniques with deterministic model, this machine learning technique in the end, they struggle if the deterministic model struggles. Like we had the same thing, like working with Jimmy on also WRF solar. So if WRF doesn't generate a cloud,
right.
To make it simple, it's very hard for the machine learning to have a cloud. So you end up with many missing predictions. No? So what we found a little bit beneficial is training machine learning with an ensemble, because if one of the ensemble members sees something, so there is a signal that goes through to the machine learning to tell, oh, look, there might be something here. While if you have only one scenario in input, it's very hard to kind of get these missing, the problem of missing values.
Great, that probabilistic weather forecasting, they haven't given us the actual ensemble members. We still have whatever, the percentile, 50th, and all these probabilistic outputs, but I think that's why it got it for this one particularly. You see, because I'm with you 100%, we saw it. WRF doesn't get it. Still, the XGB doesn't get it. And then with the probabilistic, is like, yes, we saw that there is something there.
Yeah, that's.
Thank you. Yeah, I'll chat with you about other ideas.
Okay, next.
Great talk, Marina. I'm just wondering, are the energy companies also interested in snowfall rates rather than just kind of total, snowfall at the end of an event? Have you guys looked at that, if so?
We haven't seen a big influence of the precipitation rate in the outage prediction model. It's more, two things matter: the amount of snowfall accumulated and the density of the snow, which we never have a good answer about because it's not really something that's easy. But we struggle from the outage perspective when you have you predict a very dry snow event and then you get hit by wet snow that accumulates, breaks the branches and blah, blah, blah. But we haven't seen any importance of the rate specifically. Great question.
And are the utilities using the snowfall information already? No, that's still
They're using
research.
our outage prediction system, and of course they have their own, outsourcing their weather data to DTN and other companies out there.
I got the mic. This is very interesting, Marina. There's a lot there. There's a lot of things that go through my mind, but one primarily is related to the resolution of the model. I wonder if there might be topography features that are not represented there and could be interfering with the representation of certain processes, and that's valid for both, for gust and for snowfall as well. The more you look into the model, the more you see that some of the default static fields need to be updated. And so then I also don't know if this is something that you've looked at, if they're representative of the current landscape in the area. But so I think it would be interesting to see if changing the model resolution and updating these static fields can actually aggregate anything to it, because then it doesn't really mean that you need to rerun all of the simulations, but you might incorporate that higher resolution data into the machine learning, and that could improve that.
Remember, we had a 2-kilometer operational model. When you were there, we were running a bunch of different, besides WRF. The 2-kilometer, we kind of stopped doing that because it did not show much. But of course, that's 10 years ago. I'm all like in agreement with what you say. We gotta pay a little bit more attention to that.
Okay, we have an online question from Ryan Sobash. What are the forecast lead times, and what lead times are most important to the decision makers?
Ooh, I'll start with the second one, because we had a project to convince them that we cannot provide a weather forecast 7 days ahead of the event. That's actually trustworthy. And they wanted as early as possible, especially, yes, with tropical storms, they wanted it 1 month in advance if possible, but the best one in terms of performance for us is 3 days, 2 days, and of course the day of the event, depending on the type of storm, because we have different models for winter storms, for rainstorms, for thunderstorms. So this is really depending on the type of storm. I want to say for traditional cyclones, even the 3 days, most of the times is okay. For thunderstorms, even the 12-hour ahead might miss it, so I can't tell you. I hope I answered the question.
Okay, Lulin?
Great talk, Marina. Yes, I think my comment question is sort of following Stefano's, because the model have its own behavior. If you separate your training data set according to regime, would that actually help to accelerate or to refine your output a little bit better than if you mix regimes together? That's one thought I noticed. And also for the sub-daily information, I totally think that's reasonable based on what the precipitation, the nature of the precipitation is accumulation of physics and the outcome of that whole process.
Right.
And you need to sort of learn, or at least to get the feature or the temporal kind of the feature of these other variables to give you a better location or intensity of the precipitation. So I feel like if you do have a hourly data set, would you be able to refine or further improve your predictions?
Great comments. You gave me a segue to what we are doing now and we're going to do in the future, which is we want to repeat some of that, but train the model on observations. Unfortunately, snowfall accumulation observations, as you know, are not super trustworthy. We don't have snow like SNOWTEL as in the West, but that's something we're going to try and see if that gives us a better prediction. And another study that it's almost there is figuring out which snow liquid ratio algorithm works best depending on where you are in the Northeast. And as part of that, we want to look at even doing the above freezing, below freezing, simple characterization, actually grab grid cells that do that, and then, separate it and see how that looks like. Great point. Thank you. Charlie.
Yeah, hi, Marina. I was wondering, could you elaborate on how, towards the end of the presentation, how you incorporated the probabilistic snowfall information into the model? I just didn't quite follow it.
Yeah, it was going fast. That's right. So the products that we have from NOAA are probability of exceeding certain thresholds in percentage, all of those thresholds from 0.1 to 12 inches. So these are individual features. And snowfall accumulation at different percentiles, 5th, 10th, all the way to the 95th. This is all we have from PWPF. On a 24-hour, they didn't give us anything like less than that. But I have a meeting with them next week, so maybe they can give us, higher.
Perfect, that makes sense.
What are your thoughts?
No, I just wanted to, I guess my secondary thought would be where,
Talk into the mic.
sure. I guess my secondary thought would be where are these probabilities essentially derived from?
I think it's a 50 or 100 ensemble that they are running, including NBM, the models that they have, like in the Weather Service, and I can't recite all of them.
Sure.
And they're building this. This is actually a product that they provide out.
And it's a
to
product
the
that's a
public.
24-hour lead time product. So,
Yes, I think so.
awesome.
I'm not sure. I'll get back to you on that.
Thanks.
It is already post-processed? Or?
What do you mean?
No, I mean, it's already undergoing post-processing. I mean, this product is already it already went through post-processing?
Yeah.
Okay. So you do like an additional post-processing on the top of what they already did,
No, they gave us these, I think,
Yeah, but then you use this as an input
for the machine learning
so
algorithm.
it's double post-processing.
Yeah, true.
John?
Now I got what you said, what you meant.
With like the wind gusts in particular, and probably also with the snowfall, it just seemed like the model XGBoost was like not doing good at like higher wind gusts or like the more impactful events. But in the case of wind, you kind of showed the storm, like it seemed like we had enough storms, right, to train on.
Mm-hmm.
If that's the case, then how do you do better on those more impactful events? Do we not have the right features for like those types of events, or like
I don't have a good
how do we get
answer.
around that problem?
This is still, it's an ongoing issue for us too, further like understanding what. A nice thing that we saw was the temporal resolution for snow. For gust, it doesn't matter, right? Because it is what it is, what we have hourly data. I think with gust more, when we added the New York State mesonet and this covered a larger area, gave something, not statistically important or different, but it did something. So yeah, I hear you. I don't have a good answer.
I had two questions. I'll ask them one at a time.
Be careful.
And the first one was when you do outage prediction, do you use historic outage information?
Yes,
Feed in?
OMS from the utilities
Because
directly,
it's different vulnerabilities.
which are filtered to be only weather-induced power outages.
Okay, yeah.
Yeah.
And the other one was more of a detailed question on your outputs, because the model has the ability to give you the maximum value for particularly gusts, maximum value between output times.
Yes.
So you don't have to rely on the individual output frequency.
We tried
Do you use
that.
that? Or
We did. The maximum wind at 10 meters,
yeah,
he didn't.
didn't help?
It does not fare well with the observations.
Okay.
So individually, if you take it and I don't have the plots right now, basically those direct WRF outputs are very under predicting gust because I think they're not what the observations are measuring.
Sure.
But we tried that. That's a good point, yeah.
Okay, thanks.
By the way, my group is not doing power outages modeling. Guys don't. I'm just, the weather lady. Maria knows.
Yeah, one thing I was curious about it is if you've done any work looking at aggregating the data across different scales. So like, because right now this is all like nearest WRF grid cell to location. Is that
Yes.
right? Mm-hmm. Because what we've seen in some of like the severe weather forecasting realms for like some of the like hail processing and other stuff, like aggregating over a larger area can sometimes act like, kind of like using the ensemble information. It sort of acts as spatial ensemble of features and can give you and can account for like, oh, the storm is. Worf had the storm too far north, and thus that's why it missed. So that may be worth looking into as a way to potentially bump up the skill a bit more.
Yeah, thank you.
I think for some of the other higher RET, like, I guess really getting the most intense values, I think it's just there's not much predictability at those really fine scales, because just from like, if it's a very localized gust, the time scale predictability is really small. So it's, you just may not be able to get it.
Yeah.
That's hopefully where some of the uncertainty pieces can come in. And I think they do seem to be picking up on that, which is good to see.
Yeah, thanks, DJ.
Okay, so there is another seminar in this room in 3 minutes, so I think we better cut it off here. We've had a great conversation. Let's thank Marina again.
Thank you, everybody.